So we talked about decomposing a vector into horizontal and vertical components. We're going to move into a concept called projection. You probably also would have used this in physics somewhere along the road. You just may not have known that's what you were doing. Very often when we do projection, people reference it as though it were the type of shadow it would cast if it were directly above it. And so to resolve a vector, they are looking here at vector u to resolve it and to project it onto this vector right here, v. You can imagine that you have sunlight coming up directly 90 degrees. So this is how you draw this 90 degrees straight down. And it's referred to as the shadow. The shadow that it would create would be right here. And they show the process of how they get to it. But W1, which is this guy, equals this little formula right here. And they show you the proof of it. I'm not going to make you know the proof, but I'm going to make you know this piece of it. Okay? So if I were to project U onto V, what I'm looking for is this little piece or this little shadow that would be created. The formula for finding that shadow is the dot product of the two vectors divided by the magnitude squared of the vector you are projecting onto. You're going to get a number here, and then you're going to multiply that like a scalar through the vector you are projecting onto. So your answer, your projection, is going to be another vector. It's going to be a vector in component form, in an XY form when you get done with this, okay? So what we're looking for is we are looking for this piece, the shadow, as it were, that would be created with this vector. And the shadow, or the component form of that vector, is going to be the dot product over the magnitude squared times the vector we're projecting onto. All right? And so we're going to do just a number crunching, and then we're going to do a couple word problems from that. All right? So let's look at just the number crunching piece. This is example 5. Find the projection of U onto V. It is important that you know which one's going where. U onto V. Then find the orthogonal component W such that U equals the projection of U plus W2. So what they're asking us here is find this piece. So the first thing we're going to do is we're going to find the projection. We're just going to do the projection. Now keep in mind, here's my U, here's my V. If I had sunlight coming directly here, my shadow would be here. So that's why that perpendicular is important to figure out where that shadow is. It's going to be right here. This is the piece we're looking for when we're talking about the projection of U onto V. And it's written like this, the projection of U onto V. And so we're going to use the dot product over the magnitude of the one we're projecting onto and then multiply it through. You'll notice in this particular one that it doesn't have to actually fall onto, even though it says projection onto. We're going to draw it this direction because that's where the perpendicular would be. All right, the perpendicular wouldn't be over here when it's outside on this side of it. And we're going to look at the pattern that we see with this. So the projection is actually going to end up over here. Even though it is perpendicular, it's perpendicular to what that line would be if we extended it, okay? So it's okay that it didn't fall directly onto the vector, even though it says onto. We're going to use the same formula here. We're going to use the dot product over the magnitude squared, then multiply it through. So the dot product, we're going to do the dot product of U and V. Then we're going to do this right here. All right, we're going to multiply that through. So dot product, for dot product, we're going to multiply our x's. So we're going to say -4 times 5, and we're going to add to it the product of our y's, 3 times 2. All right. So we get -20 and 6, we get -14. Over the magnitude squared. Well, the magnitude is going to be a square root, so that's nice. So we're going to do the magnitude of this guy right here, which is the 25 plus 4, but then we're going to square it. So that ends up being -14 over 29. Squaring the square root just got rid of the root. All right, so you don't have to worry about taking the root. It's just going to go away when you actually square it. That's this piece of it. We are going to multiply it through to that vector, the vector being what we're projecting onto the 5, 2. So the projection itself looks like this. It's going to be negative 14 times 5. That's negative 70 over the 29. And then 2 times negative 14, negative 28 over the 29. That is my projection. That is the component form of my little W1 here, this piece. Now it says, find the orthogonal component W2 such that U equals the projection plus W2. So they want to find this piece of it. They want to find this piece of it right here, the W2. We found the W1. They want the W2. Well, this is from part of my proof. We're trying to show that, or we're trying to find the piece that would make this true. All right. I have U. I now have W1. I'm just solving. And so if you're just solving for it, you can just put it in that format. So you can just say, well, if this is the case and I have 2 of the pieces, then the W2 should equal the U minus the W1, right? I mean, that's just basic equation solving, all right? And so that's all I'm doing here. So now I'm just saying, well, given this, I'm trying to find this, but I have the U and I have the projection and they want me to give the W2. You're just subtracting. So that's all I'm going to do. I'm going to take my U, my negative 4, 3, and I'm going to subtract the projection because I'm trying to find my W2 piece. So I'm going to subtract this guy. What do I need here? By the way, I need a common denominator. Yes. All right. So you're just going to multiply each of these pieces by that 29. So you're going to get what? Negative 116 over 29, and then negative, or yeah, that's right, negative 4, positive 3. So you're going to get a positive 87 over 29. You're going to get those, all right? So that's what you're going to get with the common denominator, and then you're subtracting. Keep in mind, too, that you are subtracting a negative. So you're going to say negative 116 minus a negative 70. I'm going to get a negative 46 over 29. Here I'm doing 87 minus a negative 28, so I'm going to get 115 over 29. That's my XY value of that one. Yes?
Will the, you said...
If I were looking at this right here, I get this component form. Negative, negative makes sense for this guy, yes? Everybody see that? Negative, negative makes sense. He should be in this quadrant. If I look at this one, a negative positive makes sense for this one right here. All right. So even if I were to put this in standard and slide it up, it's still going to be in this particular quadrant, right? It's still going to be in this quadrant. So you can eyeball it and see, does my answer make sense based on what I just did? All right. So projection is going to be this formula. And then if they want to find the other piece, you're just going to end up subtracting. You're just using this piece of it to subtract. Notice that when the u and the v is in the same direction, or the dot product is positive, then you have an acute angle, and you'll notice that it is in the same direction. So if I were to do the dot product between these two, I should get a positive number. Why? Well, they create an acute angle. If they create an acute angle, it makes sense that a shadow is going to be cast on top of it in the same direction. Okay? If I get a negative number here, then my assumption based on dot product is that these are obtuse, all right? And it also is a good logical assumption that that shadow is going to be over here, all right? And so you'll notice that when you have an acute angle or something between, or a positive dot product, then this guy's shadow drops onto the vector in the same direction. But when you have a negative or an obtuse, then that projects and drops outside of it going this way. So this makes a difference when you're talking about word problems. To get a visual of what's going on, you can look at the dot product and say, oh, okay, the dot product is this, all right? And it gives you an idea of what's going on with the problem itself. So then we have the cosine of theta here is going to be the adjacent, or what's going on with the W1, that piece. If I were looking at this angle, this acute angle that's created, I can say the cosine of him, well, that's going to be this shadow over this one that is being cast, all right? You can see that from right angle trigonometry, adjacent over hypotenuse, right? If I look over here, however, you'll notice they did a 180 minus my theta. My theta here is my obtuse angle. My right angle is actually created outside of that, but I do have supplementary angles. It forms a linear angle, linear pair here. So to find this guy, I can subtract from 180. Everybody see that? I can subtract from 180. I can figure out what this is. And that is going to be my W1 over my U, right? But you'll notice they did this. This is one of our identities that we did, remember? One of our identities. And so if I'm doing 180 minus theta for the cosine, it's actually going to throw me into a different quadrant. So it's going to negate my cosine. So I'm using a reference angle here. Does that make sense? The reference angle is going to give me inside the first quadrant. But what I need to do here is to consider the fact that I'm in a different quadrant. And so that's where this negative comes from. The negative cosine then is going to be the same thing, the W1 over the U. And then this is just manipulating it a little bit. So they just multiplied the U over, and I got a negative here. Same thing here. They just manipulated it. If I want to get the W1 by itself, I can multiply the U over. So these are just some things that are going to help you when you move into word problems. Use right angle trigonometry, demonstrates all of this. And so once we move into word problems, you're going to see this help you a little bit with your right angle trigonometry. All right, so let's look at this first word problem. Determine the downhill component of a 150-pound skier's weight that pulls the skier downhill with a slope of 30, All right, so you see that they're trying to find, and if I were to, so when I look at this visually, it really hurts my brain to figure out which one I'm solving for. If you want to, you can just think of it as, you can twist him a little. So I'll show you what I mean by that. If I were to take this and I were to shift him a little, if it will let me, right here. I'm looking for my horizontal movement, not my vertical movement. Does everybody see that? If I'm trying to figure out what effect it's having on him, I'm actually trying to figure out my horizontal effect here, if that makes sense, versus my vertical effect. Does everybody see that? That I'm actually looking at that base that I'm trying to figure out, how that 150 down pulling him is affecting his going downhill, all right? And so that's what I'm looking at when I do something like this. It's going to help me to visually see it. It wants to know what's going on here, all right? What's going on here? So that means I'm actually trying to solve for W1. You'll notice that this is an acute angle that's happening, all right? So I can go back to questions. All right, so let's try one. So when you look at this, couple things to point out. Make sure that you are checking your units. Foot-pounds are Newton meters. Remember the term joule, just in case they use it that way. They define it, and this is just the manipulation of it. All right, so this is just the manipulation of the original, and then this is just another way to write it using dot product. All right, so let's look at the example here. Find the amount of work done by Rebecca as she moves a wagon 300 meters down the beach, pulling with 20 newtons of force on the handle, which is 35 degrees above the horizon. 35 degrees above the horizon. So what pieces have they given us? All right, they have given us the force. We are using force in Newton meters, so we need to make sure they've given us this in meters, which they have. So they've given us the force, the magnitude here, and they've given us the degrees to the horizontal. So we really just have to plug it in based on the first definition that we had. We're going to use the force, which is the 20. We are going to multiply that, and this is in newtons, by the magnitude, so that by that 300 meters. And then we are going to use the 35 degrees to the horizon, the cosine of 35 degrees. All right? You get approximately 4,915 Newton meters. You can always also write this with this J, which will represent joules. All right.